Up next is Kathleen Laurini. She is on the Dynetics team, so she'll be talking about dust concerns for their human landing system. And before she gets started, I'll just note that there are two other HLS contenders, SpaceX and Blue Origin's national team, who are unable to present today, but I encourage you to go look up their architectures online if you have any questions about those. So go ahead, Kathy.
Yeah, can you hear me okay, Ryan?
Yes, I can hear you, and we see your slides.
Excellent. Well, hello, everybody, and thanks a lot for the opportunity to present to you today. When I was coordinating with Ryan in preparing this presentation, we really appreciate the opportunity to tell you guys about our human landing system and what we are doing in the area of dust mitigation. But also, Ryan opened up the opportunity for us to talk about some challenges that the broader community might be able to help with. And listening to some of the conversation today, there's really nothing new with respect to challenges we bring to the table. But as I go through them, we'll give you some insight into the things that we're working and the things that we're looking for solutions to. So again, thank you very much for the invitation. So Dynetics is leading a team of over 25 companies in developing our human landing system. So we are competing against, as Ryan said, Blue Origin and SpaceX for NASA's human landing system. The right to be able to offer this commercial service ultimately to NASA for human landing system. So the three of us are the three teams are working hard to try to advance a design and be prepared to take people back to the moon in 2024. And NASA has said they're still on track to review the work of each of the teams and make a down select end of this year or early next year. And every indication we have is they still want to keep multiple teams moving forward. So we're excited about that. In fact, right now, this week, we're in the middle of something called a certification baseline review with NASA, which is one of the two major milestones in our initial 10-month contract, where they get a really close-up look at the progress we're making in developing the requirements and all the plans that will be necessary to implement this program, as well as the conceptual design and make sure the design meets the requirements. I'll tell you a bit more about our design on a coming slide. I mentioned the teammates that we have. We have three teammates that I want to give a special nod to because they all have experience in this area. I mean, Astrobotic is on our team, and they, with their work on the Griffin and the Peregrine landers, understand the challenges of lunar dust and are helpful in our efforts. Southwest Research Institute is also on the team. They have a long history of understanding the scientific nature of the dust, and they're great to have on board. And then Sierra Nevada, as you know, has done some work before in understanding the dust and dust mitigation technology. So again, we're happy about our team. We are committed to, we are going to be one of these commercial lunar landing service providers. So we're committed to enabling a sustainable human presence on and around the moon, and excited about that future. And in order to be a commercially viable, our lander has to be reusable. So obviously the dust mitigation issues are super important to us, and we're working hard to design in to the initial lander the capabilities to make it reusable and meet the sustainability objectives of NASA. So if you could go to the next chart. Here's a picture of our concept. You see with the low slung crew module, it's a unique design compared to the others. What you don't see in this picture are drop tanks that carry most of the propellant to get the lander from NRHO, either at the Orion or the Gateway, down to the surface of the moon. So we've got very large drop tanks that carry all the propellant, most all the propellant for the descent. Those are dropped before the terminal descent, and the tanks that you see there on the outboard of the vehicle carry the propellant for really the final stages of descent, as well as the ascent propellant. You see with that low slung design, the crew is very close to the surface, and for that reason we scored well with NASA in terms of crew-centric design and all the inherent safety benefits that come from that. The crew's got a good unencumbered view of the surface out windows when they're piloting down. They've got a short ladder to climb down. It's less than 2 meters from the opening of the door down to the surface of the moon. And so we think that will really help give the crew more time on the surface, more time to be productive on the surface. The terminology we use for our system is the truss that is surrounding the crew module that you see in the middle. We call the alpaca. And the alpaca is really the bus for this vehicle. It carries all the smarts. It has the propulsion you can see. There's a lot of things you can't see. You see communications antennas. The avionics are located externally inside the alpaca. The solar arrays you see there deployed are part of the alpaca, and essentially the crew module is a payload, right? So the crew module, when we fly this configuration delivering crew, this is what it looks like. But you can remove the crew module and fly to the surface a pressurized rover or a habitat module, and even the diameter of this crew module is smaller. It's around 3 meters, but the size of the arch under the alpaca is greater. So you could fit a 5-meter diameter payload in there. And you see when you land, whatever you're bringing to the surface is very close to the surface. So it doesn't require mechanisms or complex systems to offload them. And it's easy to get things down to the surface. The first flight will carry 2 people, 2 astronauts to the surface. That's NASA's requirements, but we're sizing the vehicle for 4 initially, and we expect that the follow-on flights will carry 4. And inside the crew module, there's compartments for habitation. There's compartments for the piloting functions, the crew control, the dynamic phases of the mission, and I'll talk a little bit more about it when I get into some of the dust mitigation steps that we're taking. The lander is if you use it in a reusable scenario where you put something on the surface, our vision with a reusability cargo version of this is that the lander can pick up a payload at the gateway or in cislunar space and bring it down to the surface. So a payload, for example, that was delivered on a SLS Block 1B co-manifested with Orion can wait at the gateway for our lander to come and basically straddle it, capture it, and take it down to the surface. And in that case, the payload doesn't have to fit under the fairing of a launch vehicle the launch vehicle we will use for SLS. It can be longer. It can be a longer payload, such as taking full advantage of a co-manifested space with SLS, or it can be launched on another system to get to the gateway or cislunar space. So in that case, we can carry a lot higher mass payload, so up to 25 tons we can take down in that configuration, right? We don't need to carry propellant to lift the payloads off the surface, so that enables a lot more performance. That translates into higher performance in delivering the capability to the surface. And so, as you know, we're in a competition sensitive time. So that's probably one of the reasons why the other teams weren't here. Everybody's trying to get out the word on their lander and help people understand where they're headed in light of the fact that the competition is still going on. So let's switch now, and I want to make a couple other points before I get to the specific dust mitigation topics. But now you have a good idea of where we're headed with the Team Dynetics lander. So next page. So I wanted to also take this opportunity to talk about a vision for commercial, the expanding the lunar economy and really ensuring that there is a sustained presence. NASA has this vision where they see sustained human presence, but they're relying a lot on commercial partners to help make it so, right. Their budgets don't have a lot of money for big lunar outposts, and those are things that will come in the future. But we think the role of commercial delivery, the role of our lander together with our partner Astrobotic, we can help. We're well positioned to help realize this vision. So Astrobotic, Peregrine and Griffin, and they will be helping us to not only look for how we can accommodate small payloads that may need a ride to the surface of the moon, but also customers for large payloads. So when we design the vehicle, there are going to be places on the vehicle to attach smaller payloads. So we want to be a delivery service of opportunity for even small payloads, both external and internal payloads to the surface of the moon. And we're really happy to have Astrobotic on our team for that work. So the next page, please. So let's talk a little bit about dust. So again, Ryan asked to talk about opportunities for addressing these issues and mitigation solutions. And so obviously, I'm sure you guys have talked about it, but the sufficient availability of adequate simulants so that we can do the testing of materials and coatings and mechanisms and things will be very important. In second bullet, we know that NASA has through the CLIPS program will be carrying a number of payloads that are investigating Regolith, and will provide some insights that will help us in some of our risk mitigation approaches. So as these payloads get manifested and flown and the data is available, sharing that as soon as possible with HLS system providers, we feel will be very helpful in making sure that we get it right in some of our dust mitigation approaches. And then along those lines, promoting future payloads for CLIPS that will further understand the dust regolith dynamics and impacts due to the human and robotic landers. So is there, once we have this high traffic that we hope around Artemis Base Camp and the South Pole, and what are the impacts that we see from the flight of regolith disturbed by the landings, and what does that mean for long-term operation on the surface? Our vision for the Dynetics lander is that it may be able to carry there may be a desire to deliver payloads to the surface that could also benefit from the long-term presence of the lander. Either as let's say you deliver a pressurized rover, the lander could be a garage. A pressurized rover can go off, do its thing, come back to the lander, and recharge batteries. It can get some protection from the environment, those kinds of things. But if our lander stays for a very long time on the surface, those kinds of things would be interesting to know. And so dust mitigation technologies, of course, these things, as you've been discussing and you all know much better than I, are things that we're working on. So, things like seals and mechanisms and spacesuits and the implications of bringing all that dust in are things like everyone else we're extremely worried about. And so we've kind of broken it down into these 4 areas for now that I want to highlight. But what are some technologies that allow for exterior dust exclusion? So these are things like finishes and coatings and covers. So design approaches for excluding dust from some sensitive topics. We have, if you have a reusable lander like we do, if dust builds up on our thermal control system, our MLI or our thermal control system radiators, that can be a performance degradation issue that we don't want to see. So these exclusion technologies are important. Obviously, pre-ingress dust removal is important. You guys have talked about how brushes don't work, but what else can? There are other ideas that we've seen that are out there, and those technologies need to be advanced and advanced for the NASA suits. The suits are provided by NASA, so advanced for the NASA suits. And it certainly would be capabilities that we would fly and take advantage of. Interior dust exclusion and crew health maintenance is a concern, right? So things like filtering, things like designing in areas sort of like mudrooms, and as has been discussed before, areas to trap the dust. So we've got some clever ideas for doing that that we think will be helpful in limiting the amount of dust that ultimately gets to the part of the lander which is truly the habitation section for the crew members. And lastly, emergency preparedness for dust-induced failure mode. So basically, understanding where we're sensitive, understanding our failure tolerant situation, and being careful to design in the ability to survive these failure modes. So, and lastly, the sampling. As when we start going, we've got to get samples and bring them back, and that will provide from more locations that will help increase the database of knowledge on the regolith and the dust. So with that, I'll stop and thank you again for the invitation, and turn it back to you, Ryan.
Great, thanks, Kathy.